Hello everyone, today we'll talk about the problem number of wonderful substrings. We're given a string consisting of English lowercase letters, specifically of letters from A to J, which will become important later, and we want to count the number of non-empty substrings, so contiguous parts of this string, such that when we look at the number of occurrences of every letter, at most one of those letters appears an odd number of times. All the others have to appear an even number of times. Of course, 0 is even. So as an example, we have the word ABA. The answer is 4, because every single letter substring is indeed correct. And the substring of the whole word is also correct, because A appears an even number of times. So our allowance of one odd letter is used up by B here. But we cannot take AB or BA, because then two letters would appear an odd number of times, and this is unacceptable. Now this problem is pretty weird, but well, we're given this problem, we have to solve it. Let's begin by assuming that no letter can appear an odd number of times, so a much simpler version of the problem, where we have to count all the substrings in which every letter appears an even number of times. And one thing we can do is maintain for every letter the count of their occurrences. We're only interested in that modulo 2. So essentially a bool if it appears an odd or even number of times. And so for every letter A, B, through to J, we just mark it. For instance, a 1 here means that we have an odd number of A's, a 0 here means we have an even number of J's, perhaps 0 J's. And if we want to check, let's say, add one more letter, we just have to flip the corresponding bit in our array. So that will be our basic representation. And of course, one thing that we can do, which might be quite useful later, and it won't hurt, but it might help, is just to consider this as a single int, which will be just a bit mask, and on particular bits of this single int that we hold as a mask, we will maintain the parity of the number of occurrences of odd letters. So this is an implementation detail, and you will see it in practice, because it's typically scarier to think about it if you're not used to it than just to implement it, because implementation is pretty simple. And now if we have this type of implementation, so if we remember, for instance, we're at a given position, and we remember the parity of all the occurrences of every letter here, then how can we tell if we can create a good substring ending at this position, and how many good substrings? Well, it's very simple at this point, because if there is a good substring here, so it begins here and ends here, then that means that the count of occurrences, the parity of occurrences in our big prefix is whatever, can be anything. But the count of occurrences here, in what remains, this smaller prefix, has to be exactly equal. And it is quite intuitive, because if we have some letters appearing an odd number of times, some numbers appearing an even number of times in our big prefix, then if this smaller prefix has the same parities, then by subtracting those letters from those letters, we'll get all zeros, and that's exactly what we want. So essentially we can remember for every combination of possible parities, and this is where this alphabet being small comes into play, because those combinations are just due to the size of the alphabet. Different bit masks are possible. So we keep the count of all of those that we have seen previously as prefixes, and we push letter by letter and increment our result by the number of all the previously seen prefixes with the same exact parities, the same exact mask. Now this solves the more standard problem, so the problem where this is 0. So now if this is 1, we actually don't have to think of anything particularly smart, because if we have a mask at this position, right, and we are seeing the number of times it appeared previously, and now at most one letter would have to appear an odd number of times. We are looking here at odd letters appearing an even number of times, so let's just try for each letter to flip the bit corresponding to it, right? And check the mask with that bit flipped as a prefix, how many times it appeared as a prefix. Because that will mean how many times we had a prefix where all the numbers appeared in the same parity and one appeared in a different parity. Because if we subtract this prefix from our current prefix, we'll get all zeros and exactly one single one. So essentially we have to add this very exact mask and also add all the flips. So all the counts of all the flips. And of course, at the very beginning, when we start with the first letter, and here we just have the mask of 0 appearing one time, since this is an empty prefix. Because if we didn't have that, we would have nothing to do, right? And also we would not be able to consider a substring that is just a simple prefix. So we have this empty prefix here, and this is our starting point. And we can see that in code. So we'll create the number of times we have seen every bit mask. We've seen the bit mask 0 once, which is an empty prefix, because in the empty prefix, while we cannot count it as a result, but every letter occurs an even number of times. And now we'll keep the current mask, so the mask of the current prefix and the current result. And whenever we see a new letter, we flip the corresponding bit. So this is 2 to the power of which letter it is. So this is just, you have to choose your numbering of letters. That is probably the most useful. Now, if you are not familiar with, well, this little thing is of course XOR, because we want to flip, and flipping a bit is XOR in it, with just something that has 1 on that position, zeros everywhere else. And this means a bit shift. So we start with a single 1, and we shift it to the left the number of times that we have to, perhaps 0 times. And now we add all the previously seen prefixes with that bit mask as a result. So those will be the substrings that have all the numbers appearing, all the digits, all the letters appearing an even number of times. And then we have to increment it because we are another such prefix. And then we also want to flip a bit for every possible letter and also add them to the result, because that will mean that this very letter appears an odd number of times, all the others appear an even, right? So this is the number of times they appear, and this is one particular value that we're flipping. And then we just have to return the result.